Okay, off we go. So, picking up from where we left off last time. So, this is just another example of turning a triple integral into an iterated integral. So, as usual, we're not going to worry about where the triple integral came from. There's some application, whatever we ended up with a triple integral. We want to focus on the next step in the process, which is how to turn that into an iterated integral when the domain is a wacky shape like we have here, right? So that's kind of crazy looking. Now, the first thing I want to talk about with this particular example is how did I get this picture, right? If you look at the description of what R is bounded by, it's 5 planes. Now, how do I turn 5 planes into this picture? That's a tough question. If these were 5 random planes, this would be an inappropriately difficult question. It's just too hard, right? There's too many different ways that they can intersect on one side or the other side of some other intersection. Too much. These are not 5 random planes. There is something very special about 3 of these planes. And once you see it in one example, you'll just be constantly on the lookout for it, and you'll notice it. That's the idea anyway, in future examples. And here are the 3 special planes. There's 3 of those planes have no y's in their equation. And if y'all remember way back, right, it was early chapter 1, or I don't know, middle of chapter 1, something like that. We were talking about the equations of planes. There's no y's. It's parallel to the y-axis, and that makes them easy to draw. So that's the first thing to do. Just realize that z equals 0. Okay, well, I'm going to draw z equals 0 like this, but how did I get that? I got that because I started by thinking about what does that look like in the xz plane, and in the xz plane, this is easy. Z equals 0 in the xz plane is just a line. Right, but I know also now that the plane that this actually is parallel to the y-axis, which means it's got to go that way. And now I understand what that plane is. Does everybody see how that little clever little insight works? It makes for we're 3/5 of the way done now with this one little clever observation. Very, very cool. Okay, so we've got that, and that. And it's, I'm going to say, basically this kind of prism-looking shape that we have. Okay. All right, so then the last thing you just have to do is just think, all right, well, what does y equals 0 look like? Okay, well, y equals 0 is the xz plane. You got to think about how will this vertical xz plane, how will that intersect with our prism? And, well, it's going to just kind of cut through it to make kind of a triangular face, slice of the solid prism, if you will. And then the one that's just frankly a little bit of trouble, and there's no particularly easy moves on this one. That's our last plane, though, right? We know what everything else looks like. We just have to think about how does this one not particularly convenient plane, how does that slice through our prism? So now what is fairly easy is to look at this equation and see where the axis intercepts are. Right? So the axis intercepts are at 3 on each of the axes. And so we've got a point there and a point there and a point, maybe up there or something. And when you draw that, and now think about, again, geometric visualization, geometric appeal is all I can do here, right? Think about how that's going to kind of cut down at an angle, right? Slice through. It's not a vertical slice. It's a kind of an angled slice. And that's going to cut through and make some angled cut, resulting in an angled face. And then you clean up the picture, put it all together, and you get this shape right here. Okay, so again, 5 planes in general, way too hard. 5 special planes where you have a nice little foot in the door, still hard, but 5 planes, some of which are special, and having seen the example done, right, and having seen this trick and being on the lookout for this kind of thing, now it becomes not so bad. Okay. All right, so with the drawing out of the way, let's ask how would we go about slicing this up? And you got 6 options, and you could just start slicing away. And I'm going to show you a little bit of that, but I'm going to pretty quickly switch to a different approach. But let's do just a little bit of the slicing. Just for fun, I'm going to start by doing the dy on the outside. Let's see what these slices look like. So slicing perpendicular to the y-axis. Of course, that's what a y-slice means. And, okay, well, our slices start off not so bad. They're just little triangular cross-sections of this prism. All right. Here's the problem. I will eventually hit that corner. And after I hit that corner, the slices look qualitatively different. Now, artistic challenge. Let's see if I can do this reasonably well. Oh, gosh. Yeah, I knew I was going to mess that up. It's going to be something vaguely kind of like that, maybe. It's just hard art. But the point is it's definitely going to be qualitatively different because we're on the other side of this corner, and this sort of angle, this right face, if you will, is starting to be a part of what those cross sections look like. So problem happens at that corner, and then another problem happens at that corner, after which the slices again look different. Again, hard to draw. The details of how this is different and undesirable are less important than the fact that it's different and undesirable, right? So, okay. So that's what goes wrong if you put your dy on the outside. So obviously we're not going to do that. So we've eliminated 2 of our 6 possible slicing orders, and repeat. Right, and if you do, what you're going to find is that there's really only one good answer, and that's slicing in this order right here. And I think that's a great exercise. Think that through. As usual, if you get stuck, if you're not sure, if something goes wrong, none of your friends can help. Right, come to my office hours. I'll be happy to walk you through all the details. I'll do my best to draw a good diagram representing what goes wrong with each of these alternatives. Okay, I'm going to say arguably really a better way to think about it. So this same shape, just think about it from a projections point of view. Now, as I've already drawn on here, there's what I'm going to call a good projection to the XZ plane, and here's the shadow. It's just a triangle. Cool, no problem. As I take such slices, and as I think about what happens when I go in the y direction, coming from some point in that slice, in that sort of shadow in the XZ plane. Where's my lower bound surface for y? Where's my upper bound surface for y? Again, no big deal. The lower bound, you can see, that's going to be where the lower bound for y comes from. Always the same plane. Consistent. And then we'll see the upper bound for y is always going to be on that plane. And again, the key point is I messed up the coloring, but consistent. Always the same upper bound. Right? So if you solve for y in that equation, that gives you the upper bound for y, and if you solve for y in this equation, it will give you the lower bound for y. So it works out nice. I mean, and you can basically just kind of, as soon as you have a decent picture, of course, you can just kind of just look and see that this is going to be a good projection. Now, let's, again, just for the kind of the contrast, if nothing else, let's think through what if we tried to project in a different order, or in a different direction. So let's suppose I tried to do a projection down to the xy plane. In other words, what if I wanted to put dx dy on the outside? Okay, well, my lower bound surface is good. It's just z equals 0. But my upper bound surface, consists of two separate planes. There's this for kind of what you might say the larger values of x. This will give you the upper bound for z, but it's this back here, that back face, for the lower values of x will give you the upper bound for y. So said differently, it's inconsistent. Again, the easier way to see this, moving up, moving in the z direction, upward from this green projection, where does z end? Two different surfaces. And which two different surfaces they are doesn't even matter. The fact that there are two different surfaces makes us decide that this is not a good projection, and we don't want to do it this way, and so we move on to try something else. Okay. All right, so again, exercise. Think about what would be the projection and what would be the lower bound surface and what would be the upper bound surface or surfaces if you were to project into the YZ plane. Nice little exercise. As you might expect, it's a bad news situation. It does not work out well. Okay. All right. Last example. Now, in some sense, this is going to sort of use a lot of the techniques that we've talked about, so it's a nice sort of concluding example. We've got a region bounded by two surfaces. Now, I hope you all recognize that is rotationally symmetric around the y-axis. It's a rotation of a parabola. Think back to all those Chapter 2 methods. Right? So this is a paraboloid, and in fact, it's this paraboloid right there. And then this, again, another paraboloid, and that's this paraboloid right there. So we're looking for the region that's bounded by both of these, and this is a weird region. Oh gosh, and it's hard to draw because it's what's in between these two paraboloids. I'm going to draw it like that, but this is a bad drawing. There's no getting around the fact that, look, in between the blue and the green, there is kind of a wing of it that's kind of over here in front of this cavity, right? And then there's also kind of a back wing, if you will. One way to think about this is like a weird shaped shot glass that's been turned on its side, right? The glass part of it, right? And so, awkwardly, there's glass, and then as you continue through, looking through in that direction, then there's cavity where I'm sure water goes, and then there's more glass back there behind that, right? So how do I draw that without making it look like it's a solid? It's hard. Right, so right off the bat, this is looking like a hard problem. Everybody see the okay, yeah. Okay, hard as this is, there are certain things that kind of leap off the page at me. And one is, I look at how y is represented in these equations, given I don't even need the picture for this part, just asking myself, would I rather solve for y in these equations, or would I rather solve for x, or would I rather solve for z? Give me the y, right? I would much rather solve for y. So y is what I want to solve for, and so I'm going to put dy on the inside. I mean, that's just a guide, right? I can't guarantee that that's going to be the best answer, but it's a pretty good guide. That's certainly right in this case. Okay, the next thing I'm going to observe, we've got a good projection going to the xz plane. Because the projection, you think about how these paraboloids intersect. They're going to intersect on this kind of circular rim, if you will. Right, that's where these two surfaces intersect. And so the projection is going to be a disk down there. Not bad, could be worse. The lower bound surface, right, for a given value. Let's see if I can draw this reasonably well. Do I already have this drawn? I already have this drawn. For a given point in my shadow, looking at the range of values of y for the given x and the given z defined by that point in the shadow. Now, lower bound for y is always going to come from this point, which is going to be on that surface that has, oh gosh, I got a mess up here. Let me just clean up my mess real quick. Okay, so this point, which is on that surface, which has that equation, in which, as we've cleverly arranged, it's easy to solve for y. The upper bound for y is going to come from that point, which is on that surface, which has that equation, which again, as cleverly arranged, it's easy to solve for y. And so everything just kind of works out when you take the projection point of view. And whereas if you were to try to do a slicing argument, things would get real hard to draw. And that's a fun little exercise to go through. Set the bar low as you try to draw slices of this solid. It's hard. Worth a shot, though. Just for the experience. Okay, how are we doing? Everybody's all right? Okay. So there's a bazillion examples to, on the order of comparable to what we've talked about here. Obviously, you can look through my old exams, find a bunch of them. There's a bunch of them in the book. And this is definitely something that requires some practice. It's heavily geometric, as I'm sure you've noticed. There's the drawing aspect of things, which is just indispensably helpful not only for your own analysis, but for communicating your ideas, which is what exams are, right? So make sure you give yourself all the practice you need with drawing these kinds of figures, and give yourself the practice you need with the slicing and the projecting approaches. Both very useful. All right. Okay, so moving along to 5.5. Y'all recall that I've commented before, some of the sections of this book are enormous. And some of the sections of this book are just barely there. They're so small, right? So we saw 5.3, I think it was just like, I think we spent maybe 10 minutes total on all of 5.3, right? I think if I remember correctly, I tend to take about 3.5 lectures to get through section 5.5. It's enormous. It easily could be 2 large sections, right? So this is an Alaska versus Delaware kind of a situation in terms of size. So anyway, here we go. We're going to dive in. We'll start off with something called change of variables. I'm going to segue into change of variables by making an analogy. And in fact, this is more than just an analogy. In fact, there's a certain point of view that you can take on the substitution rule. And by the way, I know that y'all know the substitution rule. This is just writing the substitution rule as algebra. You may have seen it more as a technique. Fine, whatever. But it turns out the substitution rule is, in fact, a special case of a larger, more powerful method in multivariable calculus called change of variables. So now, in order to see how that connection gets made, or said differently, in order to use the substitution rule as a nice sort of launching point, a first step, we need to change our point of view on the substitution rule. Y'all have probably mostly thought of the substitution rule as an algebraic thing. It's, if you have an algebraic situation with an integral, there's an algebraic move that you can pull to turn that algebra into different algebra, which is hopefully algebraically easier, right? And there was no geometry anywhere in the discussion, right? So I want to view it geometrically because, again, this is what will help it extend more naturally. So, we've got our substitution where x is g of t, and rather than just writing that as an equation, I'm going to write that, with my what I call literal representation of a function. T is the input variable, so I'll draw the t-axis, the domain, on the left. X is the output variable, so I'm going to draw the x-axis, the target, on the right. And then G represents an action of taking points out of here and dropping them as images over here. Yeah? Is that cool? I didn't really do anything. I'm just sort of visualizing this function G, our substitution function. Okay. All right. Well, no surprise. A goes to G of A, and B goes to G of B. That's what G does, right? It takes inputs, gives outputs. Yawn. Okay. Now, a little bit weirder, if you think about this little interval here, this little sub-interval on the t-axis of width dt. All of those points go into the G function as well. And again, a bunch of points come out. And the bunch of points that come out, I mean, there's no promise that that's going to be the same size as the bunch of points that went in, because G is some crazy function. I don't know. It might be stretching things out in some, I don't know, right? So the nice observation, and you can think of this algebraically, and algebraically this is how we wrote down dx as g prime dt. That's just kind of how the differentiation algebra works out. I want to think of this in a different way. I want to think of dt, wrong color. I want to think of dt as representing the size of that little input subinterval. I want to think of dx as representing the size of this output subinterval, which I want to view as being a stretching of the input subinterval, right? I mean, there's some factor that you multiply by this size to get that size. And when you multiply size by a factor, I think stretching is a reasonable metaphor, right? Reasonable term. What is that stretching factor? And again, I want to think about this geometrically. Forget about the algebra. This comes very nicely from reinterpreting the size as a change, right? So don't think of this as input size, output size. Now let's think about this as representing a change in t, and there is then a corresponding change in x. We have an input change and an output change. And what is the relationship between input changes and output changes? Well, the derivative. The derivative is what you multiply by input changes to get output changes. Said differently, the derivative is our stretching factor. Everybody all right? Okay. I know it's just a different point of view on, you might say, an unnecessarily awkward, clunky point of view on what y'all previously had glass smooth, algebraic, efficient, boom boom get answers kind of method. Why are we making this clunky like this? Okay, well, this relationship that we just figured out there allows me to plug in for dx like so, and the fact that x is g of t as previously discussed, I can just plug that in like so. And notice that my original interval is from A to B on the t-axis. Well, my resulting integral is on the x-axis, dx. So the range of values of x is what I need, and that is g of A to g of B. So you can motivate the substitution rule that y'all thought of previously as being a purely algebraic construction. You can view that geometrically and visualize that as a process of taking things and turning them into other things like this. And again, this is the point of view that's going to generalize for us. Okay, how we doing? Everybody willing to sort of buy it? Alrighty, so here's the thing. We're going to do the same thing now in 2 dimensions. Now it's going to be a little weirder, and there's going to be a big question mark that's going to come up at some point that we're not immediately going to make sense out of. But as before, if you have some integral over some domain, which I'm drawing as a rectangle for reasons that I'll expound on in a couple of minutes, it doesn't have to be though. Then I can talk about, well, for a change of variables function, for some function in the place of and playing the role analogous to a substitution function, that would have some image, which I don't know what that's going to look like, but it might be weird. That's going to be the domain for my integral on the right. And I can do this same thing. X and Y are G of U and V. So X comma Y is G of U comma V. Just plug that right in. You're going to have explicit form. Once you know this change of variables function, you're going to have explicit formulas for X and Y written as functions of U and V. And you can just plug those right in to convert everything into sort of U and V language. And then there's the tricky question. Here's where things get hard. What are we going to do about the area over here? What am I going to do about that little piece of area? And the big idea is to recognize that that little piece of area, just like up here, this little piece of interval, this little length, was a stretched result of this little piece of length on the left, and we found our stretching factor by hook or by crook, but the details aren't relevant there. So likewise, that is also going to be a stretching, the result of a stretching of this little piece of area whose image it is. So we've got to figure out, we got, again, this function that takes U's and V's and gives you X's and Y's, and I need to know by what factor does that stretch areas. That's what we need, right? That's what I need to put in here. And I don't know what that is just yet. Is everybody with me? Everybody see how this is totally analogous to substitutions, to our new take on substitutions. All right. So, what is the stretching factor is the big question. I am, for the moment, just going to tell you what the answer is, and then we'll justify it later. This stretching factor is this formula right here. It's the absolute value of the determinant of the derivative matrix of, if I can get the thing, there we go, the derivative matrix of our change of variables function. That's the formula, the absolute value of the determinant of the derivative matrix. Why that's the formula? Again, we'll talk about that in a bit, but there's a lot going on right now, and I would say there's enough going on right now with keeping track of the original domain and the new domain and the various other, the plugging in, and we're gonna have our hands full just sort of executing this process, and I don't want to get off onto an abstract, discussion unnecessarily early. Okay. All right. Now, just to be explicit, the derivative matrix, of course, is that formula right there. Y'all remember derivative matrices? Oh, let's see. Okay, there we go. And then, as it turns out, there is a convenient notation that we're going to make use of here. It's very convenient, not just for saving pencil strokes, but also for interpreting certain things that we'll get to in a minute. This entire determinant we're going to denote with this math slang notation here. This is again, it's very slang. Again, I'm writing it as if it's a fraction. It's not a fraction. Very importantly, not a fraction. But it's going to turn out to behave kind of like a fraction. So it makes it convenient to write it like it's a fraction. So there's that. But the motivation for this, I think, is pretty easy to argue, and that is, well, we are literally taking the partials of x and y. And we're taking those partials with respect to u and v. And so if you were to look at this matrix, and what's the partials of x and y with respect to u and v, that's this is about as compactly as you're going to write that. And that's nice and convenient for one thing. Of course, this is not itself the matrix. This is the determinant of that matrix. The determinant is going to be a scalar, not a matrix. Another sort of convenience about writing it as a fraction, because fractions, honest fractions, which this isn't, but honest fractions are also scalars, right? So this sort of fits by type also. Okay, so very handy notation. So now last thing before we get our hands dirty and do an example, what is the advantage of writing it like this? And I'm just going to kind of put this where it goes, right there. Let's see here. Let me write this down. Let's see here. Okay, so partial xy, partial uv, and keep in mind that's what we multiply by input size du dv to get output size, keeping in mind the whole point is that that is equal to that. So dx dy, representing area in the xy plane. And so look at the little faux cancellation that happens. This is not real, and again I get the willies just in doing this, but it's as if the du dv and this partial uv, it's as if they cancel. They don't. That's not a fraction. That denominator is not a thing that could cancel even if this were a fraction. This is not a real cancellation, but it sure looks like it, and it's got an aesthetic appeal correspondingly, and some other advantages that we'll talk about later. So very handy notation. I support and encourage using this notation, however slangy it actually is. What do you think? All right. Okay, let's do one. Get our hands dirty. Sorry. One last thing I do want to mention. When we use this process, when we use this result, that these two things are equal to each other, it tends to be, all exceptions granted, tends to be most useful moving backwards. So this language pullback, the idea here is that if we were to turn the left side of the equation and then rewrite it as the right side of the equation, that would be pushing forward because that's the direction the function goes. The function goes to the right. As we're in practice actually going to do, taking the expression on the right, we're going backwards from the direction the function goes. Thus the term pullback. We pull that expression backwards through the function to get this, what is in fact going to be our new expression right here. So there's this backwardness to it, and that term pullback is common as a result. Okay. Okay, now let's do one. Okay, we are given quite a bit in the setup of this question. We're given more than we will typically be given, but again, there's a lot going on. I just want to get one into the win column first, and then we'll talk about adding complexity in a couple of minutes. We're starting off with this function right here. Notice this function takes u and v as the inputs, gives x and y as the outputs. So as indicated, u and v are the inputs, x and y are the outputs. Okay. We are also given, let's see here, that we're going to start off with the unit square s in the uv plane. So it says right there. That's going to be the left domain. And the domain that we're actually interested in is the image of that. So, this is a tricky one. Don't worry about the details on this, but you've got to kind of visualize now. If I were to take this nice, pretty little square, right, non-threatening, just a little square, but if I were to put it into this function where this is not linear, there's some quadraticness in both directions. This is still a little scary looking, right? If you were to take this and plug it into that function, you would get some sort of an output image. And I claim it looks approximately like this, and I'm just going to say, trust me on this. It's actually quite hard it's challenging. It's not overstated. It's challenging. But not what I want this example to be about. I'm going to take all of this as given in this question. Is that cool? All right. And all that said, notice what we are being asked to compute. We're being asked to compute an integral on D, namely the image. So there's our D. We're interested in this integral that happens in the xy plane. Okay, so that's the question. Now, how would I compute this integral here in the xy plane? This is going to be a hard problem. For one thing, I don't know the equations of these curves. The edges of this domain, I don't have the equations. I could parameterize them from this. I could sort of parameterize sides of the square, plug such a parameterization in to here, and out would come parameterizations of these pieces, but I don't need that. I need the equations. So I can solve for x in terms of y or y in terms of x, and I don't have that, and algebraically that too would be hard. All right. Yikes. Well, what else could I do? And my move, the really nice move. Oh, and by the way, here it's even worse. It's even worse. No matter which way I slice, for example, suppose I started slicing like this, I am pretty quickly going to hit a corner, and then as I continue slicing, I will pretty quickly thereafter hit another corner. Even if I can find the edges of this shape, I've got 3 separate iterated integrals. Nobody wants that, right? All right, so we face a very inconvenient question here. This is an ugly problem. If you just take a, 5.2 kind of approach to it. All right, so now what we're actually going to do and how we're going to turn this into an easy problem is by using change of variables. And keep in mind, we have this formula right here. This formula says that if you've got some integral on some domain that you don't like, because look at it's got corners and it's got weird curves and stuff, and I don't like it. There's my domain, I'm stuck with it, but I wish I weren't. So says change of variables. If you can view that domain, right, as being the image of a nicer domain, right, that we do like, then, well, we just do the pullback. You can just kind of, again, wave your magic wand and say, okay, pullback. And then this nasty integral that was going to be brutal to actually crank out, well, it turns into an easy integral because the domain is nice. It's a rectangle, right? Depending on how you set it up, right? Could be as nice as a rectangle. Every example is different. We'll see a bunch of examples as we go through. Sure, it's a different variable. Everything's written in terms of du, dv, and you've got to plug in the function. You've got to get rid of all your x's and y's and rewrite those in terms of u's and v's. Yeah, sure. And okay, you've got to stick in your stretching factor. Again, that's just to keep it honest. And after all, du dv is not the same as dx dy. But I can turn an ugly integral on an ugly domain into a probably perfectly reasonable integral on a, hopefully, fingers crossed, perfectly reasonable domain. And that's what we're going to do on this example. In fact, most of what I need is given in this question. We are given that our domain here, D, is the image. That was given. Sweet. We are given the function by which it is the image. That's going to be our change of variables function. We are given what the pullback domain is. It's just the unit square. So all we got to do is just use the formula on the previous page, stick in our stretching factor, and I can take this nasty, nasty green integral that this would be and rewrite it as an integral of the unit square, which is about the easiest domain you're ever going to get. Does that make sense to everybody? Okay. So, all right. It's all details from here. Oh, let's see here. We have, we're going to have to compute our stretching factor. And where's my button? Here we go. Our stretching factor, keep in mind, is that formula. So I'm going to have to compute my derivative matrix. I'm going to have to take its determinant. Don't forget the absolute values. Real easy to forget the absolute values. Don't forget the absolute values. And off you go. So here we go. Let's do it. Okay, here was our change of variables function. A couple of partial derivatives. You can find the derivative matrix. It's just this. Now make sure you can do that. Right? Remember derivative matrices from way back when, right? The partial derivatives arranged in a very particular order. You got to get the order right. Anyway, there's your derivative matrix. We're taking the determinant of it. Keep in mind that this notation, this sort of fake fractional notation, is the determinant of the matrix. It's not the matrix itself. And this is an easy determinant to compute. Easy determinant to compute. We get this right here. Everything seems to be cool. The only sort of sticky wicket is that our actual stretching factor here is not exactly that thing. It's the absolute value of that thing. So I've got to worry now about this expression. How do I deal with the absolute value of some weird, non-linear, non-simple, non-convenient expression? Everybody on board so far? Okay. And it turns out everything we need to decide whether 4uv minus 9, is this positive? Is it negative? Is it sometimes positive, sometimes negative? Oh, God, I hope not. That'd be annoying. I'd have to break up my new domain into pieces, and that seems hard. But how can I tell if this is positive or negative? Well, here's the good news. I have a crisp and clear geometric representation of u staring right at me. Here it is. There's u. I can see right here in my new domain, right? This is my new domain. U is clearly always between 0 and 1. Anybody see that? It's easy to lose track of this kind of thing. Again, there's a lot going on. We've got a lot of balls in the air that we're juggling, right? So easy to lose track, but don't forget, the whole purpose of this stretching factor is to pull the integral back to this new, what I like to call the pullback domain. And so every expression we're interested in our new integral, U and V are ranging over literally the pullback domain. Just look at it and just see what you need to see about U and V. So likewise, I can see what V is doing. V, oh, there it is. V for my entire new domain is always between 0 and 1. So now we have an easy question. UV is always less than 1. 4UV is therefore always less than 4. When I subtract 9, always negative. Yeah.
What would happen if U was like 5?
Oh, well, then we'd have a much harder problem. Yeah, and then I that's probably a kind of a situation where I wouldn't probably give you such a thing. What we'd have to do is then chop up the domain into pieces, one where it's negative, one where it's positive, and deal with them separately. Yeah, that's just no fun. Yeah. Okay, and so now that we know that this expression is always negative, its absolute value is the negative of itself. And I hope that's cool with everybody, right? Absolute values are one of these things that kind of gets de-emphasized, under-emphasized in a lot of high school math classes, certainly mine when I was in high school, and I had to really sort of buckle down and make myself proficient, comfortably proficient with stuff like that, in college, which is, again, kind of humiliating to have to think back to old ancient stuff, but that's the reality. So if you find that maybe you are a little thin on stuff like inequalities and absolute values and the whole plus minus thing, square roots, and there's a bunch of sticky little things there. Now's the time to straighten all that out. And by the way, I do have a video on that. If you just want to hear my take on a lot of these little annoyances, algebraic annoyances, I have so YouTube channel, miscellaneous topics playlist, and the recording is called Algebraic Pitfalls. So, might want to take a look. Okay, so we're in business, and it's all over with the shouting. We started off with this, again, highly undesirable domain over which we wanted to do some integral. That's going to be hard. It's going to be hard, right? But we did the pullback, and all we had to do, wrong color. All we had to do was basically plug in, observe the new pullback domain, and then insert the stretching factor. And you can see I've got my stretching factor that I computed there. There it is. There's our stretching factor. Everything else is literally just plugging in the formulas I was given. So in particular, I was given, and again, easy to overlook. Very easy to overlook this. I was given a formula for x. Because x is the first output of g, I have a formula for the first output of g. So that's what x is. And so notice all I've done here is just plug that in. What is x? X is that thing. And then likewise, what is y? Well, y is the second output. I have a formula for the second output. So this y is that thing. Got ourselves a new integral. And let's see here. Let me get rid of all of these marks. Deleting. Now let's real quick. We'll call it a day in just a moment. Which of these integrals would you rather do? There's that one, And there's this one. A lot of students will make the mistake of looking at the integrand. And the integrand is rarely the problem. When you're looking at multivariable integrals, the problem is usually the domain. And so, sure, I'm going to grant you that the integrand on this new pullback integral is not as nice. Fair. Sure. But you look at the domains, and it is no contest. Right? Let's see again if I can. Yeah. So this integral here is on a great domain, and this seemingly, superficially better integral is on a much less desirable domain. So I say go green on this choice. It's way better. Again, world's simplest two-dimensional domain. What's easier than a unit square? 0 to 1, 0 to 1. Couldn't get any nicer than that. Doesn't even have any fractions in it, right? Awesome domain. And that makes this integral on the right actually quite easy to compute. Okay, so we turned a brutal problem into an easy problem. That's the big point of change of variables, right? So all of this, this generalization of this substitution concept is so that we can turn hard problems into easy problems. And we'll pick up here on Monday. Y'all have a great weekend. See you later. Don't forget about attendance, of course.